Right, so I think we'll start now. This is the final session. We've had one talk pull out, so we're moving everything forward and we'll have lots of time for questions and discussion at the end. So first off is Juliet Biggs, who's missing bits of slide. Will you take a minute?
No, it's just that slide. You don't know why the other ones look okay. All right, we'll keep going. And if there's any other, if that happens again, I will tell you what's missing.
Okay, I'll give you 2 minutes, but you can take your time. Okay.
All right. Okay. Thank you very much. So I realise, to my horror, that this is almost exactly 20 years since I first came to Fringe. And back in those early Frascati fringes, we spent all our time asking ESA for more data. And actually, look what happened. They gave us a lot more data. So the LIXAR Volcano database, Sentinel-1 INSAR data, now contains over 2 million different images of volcanoes, and that spans more than 1,000 volcanoes around the world. And this presents remarkable opportunities for understanding magmatic systems on a global scale, and also for monitoring and forecasting in the short term. But there are lots of challenges associated with basically the size of the data set, particularly to do with expert interpretation and timely dissemination. And a real theme of this Fringe meeting has been people turning towards machine learning and deep learning tools in order to address these challenges. So what I'm going to talk about today, and actually the next couple of talks following me, are all about some of the machine learning and deep learning methods that we've been developing within COMET, and I'm going to talk specifically about the ones we've been developing at Bristol. And the talk is divided into 2 parts. The first one is really now an operational system. It's a convolutional neural network that we developed with Pui and Fabian back in a series of papers in 2018, 2019. And I'm going to update you about what we've been doing to deploy that on a much larger data set and in an operational sense. And then the second part of the talk is introducing you to some new methods that we're developing, new architectures, new applications, and new catalogs. And these are very much in the proof of concept stage. These are a long way from becoming operational. So a quick recap of this deep learning framework for the detection of volcano deformation. So it's based on a transfer learning principle. So there are lots of networks that have been developed and trained extensively for looking at photographs. And a favorite task is identifying pictures of your pets. So this particular one I'm showing you here has the probability of this picture being a probability that it's a picture of a dog versus that of a cat. That's not terribly useful for our particular application, but what we can do is we can take away this upper layer and we can retrain it with some information about volcanoes. And we found the best way to do that is a combination of real examples, real interferograms, and synthetic examples of what we think both deformation and noise really looks like. And we also need to have a balanced training data set that has both positive and negative samples. So this training process is pretty slow. It requires an HPC, but once you've got the model trained, you can actually apply it to large numbers of images very, very quickly. And so what we do is we divide our interferograms into patches, we run those through, we merge them back together, and we get something that looks like this. So in this image, we have an interferogram shown in grayscale. The yellow colors represent the probability according to the CNN, and we have contours of probabilities of 0.5 and 0.9. So this was developed on a LIXAR test dataset, which consisted of about 30,000 interferograms. It seemed huge at the time. By 5 years later, it actually seems fairly small. But we had a classification accuracy of 0.981 and a detection threshold we estimate to be something like 3 or 4 centimeters, depending on the conditions. So basically, you need a couple of fringe or more to be able to do this. So what I'm going to talk you through now is how we've tried applying this on a much larger scale, and there are 3 steps here. So the first one is the automatic processing needed to provide the data set. The second one is the detection, and the third one is the expert review. And don't try and read all this because I'm going to break it down. So the first bit here is the automatic processing, and we're using the LIXAR system, as you might expect. And what I'm going to show you is a much larger data set than the proof of concept one. It consists of nearly 600,000 images spanning the first 5 years of Sentinel-1. And what's important here is that it has a much greater global coverage than our proof of concept data set did, and also that it now includes some long-term interferograms, which turn out to be really important, as you'll see later. We then run this CNN through the data, and it flags up 3,000 images of 366 different volcanoes. So this is a positive rate of less than 1%, which is actually, we've really reduced the size of the data set that we have to look at, but it's still quite a lot of images to look at, and that's only going to increase with time. So we need a strategy for dealing with this. And what we do is we look at the number of positives per volcano. And that's what the histogram here shows. And there's a kind of a natural divide here at about 25. So the volcanoes with more than 25 flags tend to have very high probabilities. There are 16 of these. And the volcanoes with less than 25 flags generally have lower probabilities. And we can treat these two types of behavior in different ways. And I should also say we throw out any of the flags that use only one flag per volcano. Because of the redundant way we do the processing, any real deformation signal ought to get flagged 6 times. But we throw out anything that only occurs once. So once we've identified these volcanoes, we can look up external information. The GVP, for example, records information about seismic swarms and other kind of changes that might be observed at the volcano. We can look that up. But also for the persistently classified volcanoes, we can carry out time series analysis. So the actual displacement time series is shown here in blue, but we can also run each epoch of this time series through our CNN and find out where the flags actually start. The examples I've shown here are 2 eruptions, and the red time series, which is the probability from the CNN, clearly jumps up at the time of the eruption. And we can also apply some atmospheric corrections. So when we were doing our proof of concept studies, one thing that we found very effective at distinguishing between false positives and true positives was using an atmospheric model. It's the one thing that really still confuses the model in some cases. So the example I'm showing here is from Fuji, which had a lot of detections. And actually, if we look at the time series, you can see it's clearly very seasonal. If we apply a Gakos correction, we reduce both the seasonality and the number of detections. So this is what we would think of as a false positive. So what did we find? Well, as you might expect, the data set is dominated by large deformation events. And in fact, it's almost completely dominated by the Galapagos. Over a third of our detections come from there, including over 900 from Sierra Negra. There's actually 2 reasons for this. One of them is there are a lot of actively deforming volcanoes, as Susie showed us earlier. But also, it's a wonderful natural laboratory for INSAR, so our LIXAR data set is really up to date. And so there are an awful lot of interferograms in this area for us to look at. But we also detect some other eruptions and intrusions, and between them, Kilauea, Tal, Etna, and Artele account for another 150 of these flags. But we were very happy that we could actually start to detect slow deformation events that are not associated with eruptions or intrusions. And these 2 examples are Laguna del Maule and De Moyo, which are slowly deforming volcanoes in the high Andes. The reason we can detect these is because we now have these long duration interferograms. The figure at the bottom here plots each one of these images according to duration and coherence, and the color of the dot represents the probability output from the CNN. And you can see all of these flagged interferograms are these long duration summer to summer coherent interferograms. So they're really important for picking out these slow deformation events in our data set. So just a quick recap of some of the other signals that we picked out that might be of interest. So Tambora here, previously no deformation had been reported at this volcano, and in fact ESA had stopped collecting data over this track, bizarrely in the middle of 2018, but we actually see subsidence of 8 centimeters a year, and this is actually quite significant. This is the site of the largest known historical eruption anywhere in the world, so this is quite alarming, and actually the time series has now been continued since then. And then we found Reykjanes Peninsula was flagged in quite a few, or flagged many times, actually for 2 reasons. One of them is the pre-eruptive signal for what is an ongoing eruption there, which we caught before the eruption started, and also the geothermal plant was flagged a large number of times. But we also detect non-volcanic sources that generate fringes. So Rinjani here, the reason that was detected wasn't actually anything to do with the volcano itself, but there was a nearby magnitude 6.9 earthquake that caused a lot of detection. And at Kjærfjord, actually the fringes we see are the ones associated with the edge of the ice cap rather than anything volcanic. So this system now runs automatically on every image processed by the LIXAR system. The big frames get processed, the volcanoes get cut out, and the system automatically runs a CNN and outputs a probability. And that information is shared through the volcano deformation portal. So if you go to the front page, you can see a list of the most recently flagged volcanoes here. And I did this just last week. Kilauea came up top. I clicked on Kilauea. It gives me a time series over here of all the different probabilities. It gives me the mean and the maximum. So I picked out a couple of times to show you. This is one here where there were a large number of flags, and you can clearly see the deformation signal that's picking up. And this is one where there weren't any flags, and you can see why there's nothing very interesting here happening. So this system, I would say, is now pretty much operational, but it's not perfect. So what are the next steps? What else can we do here? Well, one of the challenges, I think, with this system is that it's trained based on what we think the deformation signals we're looking for look like. And we actually don't really have enough examples. If you consider all the geologically plausible types of deformation signals we've got, our sampling of that is actually very small. And we've got around that by using a combination of data augmentation and synthetic training. But ultimately, that is going to bias our catalogue to looking for more deformation signals that are like the ones that we've seen already. One thing we're doing is developing unsupervised learning. It's called anomaly detection. So in this case, what you do is you train your model to understand the noisy conditions at a particular volcano. So it understands what all the noise looks like in your signal, and then it detects if something unusual happens. So here we have the unlabeled training data set. I run it through your model and it learns the average features. Then you can put in some test images, and what it calculates, the loss function it calculates is the difference between these test images and the average features that it had of the data set before, and it can then flag them as normal or abnormal. If you want to see some examples of how well or how badly this works, then I encourage you to go see Robert's poster in the poster session tomorrow, or even in the coffee break. Another approach that we're using is semi-supervised learning. This is sort of a blend of these two. So in this case, we use contrastive learning, which we input in the entire data set, and it learns the characteristics of that data set. And then you can train your detector with a much smaller number of labeled images. And once again, if you want to see how this works out, go see Pui's poster in the poster hall and see if you can find out whether this performs better or worse than some of our other CNN. But we're also looking into other types of applications of deep learning. And one of them is that one potential application is denoising. So we've heard a lot at this conference about the types of corrections you could apply to your data. But actually, can we train a deep learning model to do those corrections for us? This is a very simple example. This is possibly not even proof of concept yet. But what we've done is train the model using some images before and some synthetic deformation. Then we run it through a UNet architecture, which has two decoders, one for looking for the deformation and one for looking for the noise. What we're showing on the right here is synthetic data, and it works very nicely on synthetic data, but we haven't really tested it extensively on real data yet. So this is our input ground truth, then we add some noise to it, we run it through the model, and we can actually see a nice clean output, and this is the noise signal that it's removing from that. So I think this approach has a lot of potential, but we need to do more work on it. And another thing that I think is a really interesting machine learning, but not quite deep learning application, is to separate out different signals. So if we take a step back and think about volcanoes, we know that most volcanoes have lots of processes operating at the same time. And a really classic example are caldera systems where we have deformation associated with the magmatic system and deformation associated with the hydrothermal system happening at the same time. And there was a really high-profile series of papers back in the 2000s that tried to separate these signals using gravity. And they never really came to a conclusion about what deformation was magmatic and what was hydrothermal. But actually, we now have sufficient data from missions like Sentinel-1 where we actually have a chance of being able to separate these signals out because they have different patterns in space and time. We would expect to see different behaviors between them. And so Edna has been trying to do this with ICA, and then also a sort of a clustering algorithm here. This is Matt Gaddis's algorithm. And because we are trying to differentiate the signals based on their spatial patterns, our hypothesis is that the hydrothermal system is structurally controlled. So it would have a structurally controlled pattern, whereas the magmatic system is deeper and probably wouldn't. We run the ICA in a spatial mode. And these are three components that we pick out. The first two are still slightly mixed together, but we can see the magmatic signal, which is really dominant in the data set. We can also see some topographically correlated signal, but most importantly, we can see this signal on the right here, which this east-west structure comes out very clearly, and that is from what we know of the structure and the hydrothermal system at this volcano. That is the hydrothermal system that we're picking out, and it's orders of magnitude smaller than the magmatic deformation. So we can actually start to separate these signals based on their spatial characteristics because we have enough data with Sentinel to allow us to do that finally. And then I just wanted to say a few words about sort of the final aims of, why are we trying to do this on a global scale rather than trying to understand each volcano on a really case-by-case data basis. And actually we've put together, I've been involved in several kind of compilations over the years based on metadata, and we've learned a lot about magmatic systems, their links to it, the statistical links to eruptions, and the architecture of magmatic systems by doing this. But these are all based on metadata studies. Everything was processed in different ways and modeled in different ways, and it's a bit of a mishmash, and that always limits the kind of level of interpretation you can put on it. So hopefully by using these systematically processed, systematic tools, we can actually build a much better catalogue that we can use for things like identifying analog behaviours of magmatic systems that are really useful for forecasting and really useful for understanding the characteristics of the systems in a global scale. So towards that, we're not using the full global machine learning catalogues yet. We're using a really nice subset of data that was put together by Fabian Albino that covers the whole East African Rift. So this is still 4,000 interferograms, 64 volcanoes, of which 16 have high signal-to-noise signals. And we're trying to classify these in the way that you could put the data into a catalogue. So the first step has been to look at these in time, and this is work that Fabian published last year. So for each of these 16 time series, we fit two models, one linear and one sigmoidal. The linear represents steady state behavior. Sigmoidal is not really meant to represent any particular physical process. It just allows you to capture the magnitude and the duration of the signal of that volcano. And we fit both models to the data, and then we use AIC to judge the goodness of fit for different models because they have different numbers of parameters, so we can't compare the readings to that. And what we find is that of these signals, 6 are best fit by a sigmoidal model, which means they have transient deformation. 7 of them are steady state, and another 3 are actually linear with a seasonal component added on top. And we can extract the parameters from these simple functional fits that allow us to build up a catalogue. The final stage in this process, or the next stage, I should say, not final, the next stage in this process is to actually think about the spatial patterns of these deformation signals. Once again, this is the same data set from Fabian, and you can see that the hugely different spatial patterns here. At the moment, we're doing this by trying to extract the source parameters using an inversion approach. And if you want to see more about that, go and see Ben Ireland's poster in the poster session. So that is my conclusion, and I should probably stop to allow for some questions. Yeah.
That's exactly on time. All right, thank you. Here's a question for Juliette. Can we get the microphone up to Paul's hand went up first? Immediately.
That always makes me nervous.
No, I just wanted to beat out the competition. No, so one question I had is, so these are being done for ascending or descending independently. You're not kind of cross-checking them?
Yes, at the moment we're just doing each interferogram, no matter where it comes from. And actually, for the operational system, we don't even care which volcano it comes from. It's just a whole bunch of PNGs. They could be from anywhere.
I was thinking that, as humans, when we get something in a volcano, typically you say, well, let's confirm it by looking at the other track, just to,
Yeah,
make
yeah.
sure, especially for atmosphere.
Yeah, and I think that probably is the direction we're going in. So we're starting to already compile the data per volcano, build time series, apply these methods to time series rather than individual interferograms. And I think building in multiple time series at the same volcano is a logical progression.
Okay, great.
Do we have one more question? Okay. Okay.
Folks' question was, am I looking at wrapped or unwrapped interferograms? For the CNN that I showed you, that is all wrapped individual interferograms. Some of the other methods I'm showing you are using unwrapped data and moving towards unwrapped data, time series, atmospherically corrected. But the original one, actually when we started doing this, we didn't have unwrapped data, we didn't have time series, so we started off with the wrapped interferograms.
Well, I think it's better to look at
Well, absolutely, but it depends which model you're using, which works best. So our system was designed to work very well on those, and that there's certainly advantages to that. But for other systems, it's a bit better to work on unwrapped data for sure.
All right. Thank you, Juliet.
Okay, let's move on with Danny Huber. He will continue with machine learning and classification and forecast.
Okay, well, thank you, Juliet. I think that's nice introduces my talk as well. So I'm going to talk about sort of moving beyond the detection and classification to forecasting, although I will touch on detection and classification as we go along. So this work is also under the banner of COMET, but I'm particularly focusing on the work that's going on from the Deep Fog team. So this is an EU project, EU-funded project that we're working on for the next, well, it's a 5-year project. We're a couple of years in already. As I go along, I'll just be sort of flagging up other people's presentations and posters that you can go and get more detail from. Okay, so this was kind of motivated by the field of video prediction. So this is a computer science field where people could take a couple of frames and then predict what happens afterwards. So in this example here, it's not our example, it's just one I've taken from the web, but just the first couple of frames here are used to predict, right? So when it goes yellow, that's already a prediction. So you can see just the first couple of frames are used, and then there's several different models here showing how a human continues to run across the page. Okay, it's not perfect, but it's doing quite a good job. So it's motivated by that, and you might ask why we want to bother to try and predict deformation or forecast deformation. It's mainly as a tool to be used by volcano observatories. So it's an extra tool that could be used to maybe inform what may or may not happen. So in principle, if we have a database of actual deformation maps from INSAR, we can feed them into a deep learning network of some sort and train that deep learning network. And then during a forecasting stage, we can take a whole bunch of recent deformation maps, feed them in, and then the deep learning network will spit out what might happen next. So this is a case of real data where there was a dike propagation, and the forecast might be, so we want to give actually more than one forecast, but the forecast might be that actually the dike stalls, or it might be that the dike actually propagates and leads to an eruption, right? So, and we'd like to assign probabilities to these various different scenarios. So the idea is that, if you take data, you train this on data from lots of volcanoes, you might flag up things with individual volcanoes that may not immediately spring to mind from the past experience of those volcanoes. Okay, so this is kind of the idea. Unfortunately, we just don't have enough. Although we have lots of sentinel data, we don't have enough examples of actual time series of deformation. So lots of examples of individual interferograms of deformation, but the whole time series, we're actually a little bit limited. So we're relying a lot then on simulated deformation maps. And actually, this is kind of the bulk of the work that we've been focusing on, is actually how do we simulate data well to try and be as realistic as possible. Okay, first of all, I'll talk about the work we've done on the real deformation maps. So as Juliet mentioned already, the LIXAR project, we actually processed a lot of data. Up to now, I think I've just looked a couple of days ago, and there's like almost 1.5 million interferograms that we processed around the world over straining areas and volcanoes. So most of these interferograms are over straining areas, of course. And there's an awful lot on volcanoes as well. We take these data, as Julia also mentioned, and we process them in a time series manner. And sometimes that's tricky, right? So you get all kinds of problems with these data. So automating this process to process large amounts of data has been difficult. With some of the problems mentioned here that we've had. But nevertheless, we can eventually get out a product which gives us a time series of information. So if you want to see more details on this, you can go and see Milan's poster, Milan Lizeski. Unfortunately, I took these numbers from the program, and it turns out when I looked yesterday that the numbers don't relate to the actual numbers that we posted. So just ignore all the numbers in this presentation. Okay, and just an example from the tectonic realm of the kind of product we can get out in the end when you process huge amounts of data. So this is the whole Tibetan region showing the east-west velocities from our data, combined with GNSS, I should say, in this case. And you can hear more about this from Tim Wright in his talk tomorrow. Okay, but back to volcanoes. So we already had this processing, this sort of standard processing, but we realized for the kind of time series we need a slightly, improved time series in a number of ways. So one is in terms of resolution. So we've gone from our kind of standard 100-meter resolution product, and we're now working at 30-meter resolution for volcanoes. That's one example. This is just one example of the time series we get out. And of course, it can be quite variable, right? Typically not linear. So in comparison to the strain rates and things, where things are a little bit easier, at volcanoes, we have to worry about more regular processes. The other issues, like lots of volcanoes have snow or vegetation on them and so on. So we've also worked hard to kind of pick out the best subset of interferograms to use. So by looking at doing a coherence analysis, it's just a coherence matrix for one volcano, the Hecla. So for this one, in fact, what we do is we just take the interferograms during the summer, the Northern Hemisphere summer, and make small baselines during the summer, but then longer ones from summer to summer. So it's obvious what you need to do, but there's some legwork to do this for every volcano. So Lin Chen already gave a talk about this, so there's many other improvements that she's worked on, and I think you can still go back in time and watch her talk. She gave it on Monday, but if you go to the Fringe site, you can still see that. Okay, so I've just got one slide on this. In fact, just with the data alone, we can already do some detection, of course, and this is something that Matt Gaddis has worked on. Unsupervised machine learning, we can just be applied to this in our time series directly. And so we developed an algorithm. Essentially, what we want to do is flag up new deformation. So it's a little bit different to the aims of what Julia was talking about. We just want to flag up when deformation rate changes or the pattern of deformation changes. And of course, this has to work when we have slow onset, and also has to work automatically. So in the next talk by Matt, you'll hear more about this then. But back to the deep learning. So yeah, that's the real deformation maps. So first of all, we're working with Sentinel data. That makes sense. Of course, we'd like to trawl through all the data archive, so look at all the other missions that we've had over time and still have now, and gather as many examples of these as we can. But nevertheless, we're still going to need these simulated data. So for our initial simulations, we've only used very simple sources. So what we do is we take simple deformation patterns like sills and dikes and so on, a few examples here, and we add some atmospheric phase screen that's correlated with topography. We also add some turbulent topography, turbulent APS. We mask some of this because typically we get bad coherence in some areas, and then we get a bunch of simulations like this. So we can generate as many examples of this as you want, of course, which is quite useful. This is another thing actually that Matt Gaddis has worked on, is using a so-called two-headed convolutional neural network for simultaneous location and classification of deformation. So again, it's a little bit different because it's well, in some sense it's the same, right? It's doing location of deformation, but also a little bit of classification as well. As Juliet talked about. So this is some examples of the results. I'll just focus on one here just to guide you through it. So what you're actually seeing here in the red is the results from the CNN, the network, and in black you're seeing the truth. So in terms of location, you can see it's approximately the same. So these are real data, by the way, so these were used for testing, not for training. And then also in red, you can see the sort of probability for the type of source. And also in black, you can see what an expert has judged to be the truth for each case. So generally speaking, this does a pretty good job in terms of categorizing into kind of simple dike versus sill versus no deformation type classification. Another thing we can do with these rather simple models is actually kind of automate the phase and wrapping processing using a convolutional neural network as well. And so Eilish O'Grady has been working on this. Essentially, it works by taking the wrapped interferogram, feeding it into the CNN, and then actually what it does is calculate the ambiguity gradients. So the integer ambiguity gradients, you probably can't see them very well, but they're in the x direction, the y direction on the right here. And then there's a further step then to sort of integrate these to get the actual unwrapped interferogram. So you integrate the ambiguity gradients first, and then you can just apply them to the wrapped data and get the unwrapped results. So I guess what works really well here is actually to do this in a probability-based way. So I think it's similar to what we would do. I've always been intrigued, right, because we can look at interferograms and judge really well when it's wrong. Do it by eye much better than any of our algorithms. So it's trying to simulate that. So when we find our own paths with our eye, sort of based on probability. So it's trying to simulate that, and it seems to be working quite well. So again, there's a post on this as well. You can go and catch up with Eilish tomorrow or later today. That's right. Come in. You've either got to go.
Next one round.
Come through. Okay. Okay, but coming back to this idea of forecasting, we can't rely on these sort of simple models. So this is the kind of model that I've looked at so far. This would be an example of a simple cell that's just inflating in an elastic half space. But of course, real volcanic systems are much more complex. Something like this with maybe liquid magma distributed through a magma rush system, stretching down to the core mantle, down to the mantle boundary. So how do we deal with this? One of the things we've done to start with is just trying to characterize by looking at all the examples we can of deformation, to try and characterize the kind of temporal evolution. So this is an example of 3 uplift episodes. And if you look at each of them, it turns out in all cases, you can actually, after some time, they become logarithmic in nature. So this seems to be a fairly ubiquitous process. So of course, this helps us to guide our simulations in the end. So this is trying to characterize the behavior of volcanoes by looking at all the data we can. Now, to explain this, the only method, the only process we've come up with so far that can explain this is some sort of flow through poroelastic medium and relaxation and a poroviscoelastic medium. So in this example here, if you look at the black line, that's just showing a logarithmic uplift, and the blue dots are showing the poroviscoelastic solution. In this case, it's just a liquid magma surrounded by a poroviscoelastic shell. So again, there's a post on this as well by Camilla Neveu, so I encourage you to go and see that. Okay, so I think that it's fair to say that from what we've looked at so far, we expect porous flow to be an important process, but actually we don't expect it to be as simple as that. So we're also working on more complex models which are trying to simulate better the kind of magmatic systems we might have. So this is a sort of first go at that. This is using COMSOL, so it's a finite element model. and we're using the viscosity is based on the temperature, so it's a thermally dependent viscosity structure. Again, we have poor elastic magma mush zone, and then we're injecting magma from below. And then we're basically varying the range of the parameters. So there's lots of parameters in this model, so we've tried varying them within reasonable ranges, and these ranges come from all kinds of other fields as well, mostly from other fields, I should say, rather than from the field of deformation. So we can kind of characterize the range of deformation we can expect at the surface in these kinds of models. For this, I encourage you to go and see Rachel Bilson's poster tomorrow. Okay, and one other thing we can do is actually then try and modify these models to actually fit real data. So you've heard about ASCIA both this morning and this afternoon already, so I don't really have to explain it, but it was subsiding for a long time, and then recently it's been uplifting. So we're modeling this in a, well, we like to think a more realistic way, right? So going beyond elastic modeling that we've worked on already, and trying to include poorer viscoelastic processes. Of course, a lot of these things are not very well constrained, but you can go and see Josefa's poster if you want to learn more about this. What time did I start? Okay, all right. Okay, so then we come to the actual deep learning training. So I have to say, up to now, we've really been focusing on these other aspects, and we really only just had started working on the forecasting. But I'll show you what we've got so far. So we've taken as training data just one example of propagating dikes. Of course, eventually we want to actually kind of simulate and forecast all the kind of processes you might expect of volcanoes. But we've started with propagating dikes. So we can simulate dikes. We can add some realistic looking atmosphere, as is done here. So you can see the dike up in the top left-hand corner, and it's gradually propagating in these 5 interferograms. And then we can use these to train a long short-term memory, an LSTM network. And essentially what we're trying to do is produce the last 3 of these interferograms, but only the deformation, and then forecast or predict the next 2. That's what's been shown here. So these are on the same timeline. So we don't worry about the first 2. We're trying to essentially filter the first 3, so to get the deformation out, and then predict the next 2. So these are just this is one. I'm going to show you one example of some preliminary results from this approach. So these were the data that were put in. So these are testing data now, not training data, of course. And this is the output, right? So what you can see is a kind of filtered, not perfectly, but a kind of filtered version of these 3 interferograms looking at the deformation. But then the final 2, these are the prediction of what would happen next. And because these are simulated data, we know what happens next, and we simulate it ourselves, so we can compare that to the truth. So overall, these I think these are kind of reasonable preliminary results. This, I should say, this is really Matt's work. Rather informs me a transform approach is likely to do better, and of course, this is it's an ongoing field of well, I guess of a lot of research in computer science, so we can take advantage of that. So eventually, we'll need to expand this, simulated data to include, first of all, be more realistic, but also include deformation processes, all deformation processes of volcanoes. And by the way, that's not just magmatic processes, of course. There are plenty of other processes that happen in volcanoes. And then one other thing that we're going to explore is the addition of physics to our neural networks. So this is physics-informed deep learning. The advantage of that, of course, is if you know something about the physics, you can constrain basically the range of possible model outputs, and in the end, you can use less training data as well. So I'll leave it there. I'll just put my summary up. Yeah, I'm happy to take any questions.
Who's got first question for Andy?
Yeah, Thank you, Andy. I was wondering, so yeah, of course, you start with simple case of the dike propagation, and it's like something linear, or like the steps are like kind of easy to predict. I was wondering, in the case that your dike will stop to propagate or something more complex, like, do you think your machine learning will learn to or be able to predict that?
Yeah, so I mean, yes, it wasn't quite linear. There's some curvature in there, but yeah, you're right. It's a simple case. I mean, it depends on your training data. So if your training data include that, then it can learn that. And it gets back to this idea as well. In the end, we don't want just to predict necessarily one outcome. We can actually predict a range of outcomes. So in some, it might actually predict that it stalls. These are very simplistic simulations. Eventually, we can include simulations that really are based more on the physics. So you can, I mean, they're out there. If you look at Eleanor Vals's work, you can kind of predict where dikes will go and so on. So we can use those kind of simulations, and that will include stalling in some cases. So yeah, in principle, it should work.
I think Volk has a question.
For the dike, of course, if you have to wait the sentinel for 5 interferograms, you have to wait quite long. By then, the dike has erupted since long. So it looks to me that this could be really cool if you get ice eye, or if you go to daily images, then these kind of propagations or calculations have been done before humans can do it. Yeah, that's a really good point. And yeah, I mean, we're working largely with sensible data for obvious reasons, because we can. It's freely available. But actually, when it comes down to something actually happening in a volcano, of course, we can then take whatever data are made available, and it may well be ISI data with the one interval. So yeah, that's a good point. I mean, in principle, we don't have to wait for 5 images, right? This is just our first attempt. But I think some processes will probably want an even longer time series to try and figure. So if you had a long-term uplift, for instance, and you want to predict when something's going to happen, it might be months or even years later. So the time series you might need could be quite variable depending on the process. But that's something we need to consider as well, I think.
Right. Thank you, Andy. I think,
All right, thank you.
right. So, great. Our next talk, you've already had a spoiler for, from Matt Gaddis. He's going to give you a bit more about the Lix alert algorithm.
So, hi everybody, I'm Matthew Gaddis, and I'm going to be talking about how you can use independent component analysis, or ICA, with time series of INSAR data to monitor volcanoes. And before I begin, I'd like to acknowledge my co-authors shown on the side of the slide, and also the funders of this work. And also a really quick acknowledgement of all the brilliant open source and free software that I use to do this work. So, why do we want to automate the detection of volcanic unrest with Sentinel-1 INSAR data? Here's a quick image of a LIXAR interferogram processed automatically for the Galapagos. You can see there's the relief shading of the DEM, some areas of incoherence, but at the bottom, at Sierra Negra, there's a really clear deformation signal. So even though these deformation signals can be quite obvious or apparent, the search for them in a huge amount of data can be really time consuming and not possible for a human to do. So we could zoom out, and I show the Galapagos and the Eastern Pacific here. So volcanoes are red triangles, and the green are LIXAR stacks of interferograms. The darker ones mean we have a bigger stack. So looking even at just this small region, you can see that we have a huge number of volcanoes with a huge amount of data, and it all updates every 6, 12, 24 days. So it's just too tricky to look through. I'd also like to say that if volcano monitoring isn't your thing, the algorithms that we've developed, I think, really interrogate what's going on a volcano. So if you've got a stack of time series, for one of the volcanoes you're studying, then please, I hope that the algorithm we present would allow you with a tool to do a sort of case study on that specific volcano. It's not just about monitoring lots of volcanoes. Previously, we've published a paper in 2018 where we had a prototype detection algorithm. We looked at independent component analysis at Sierra Negra. That's the independent component that captures the deformation, geocoded in Google Earth. And at the top, we show that we were able to track how this component was used through time. And then as the colors switched from, say, yellows, oranges to red, that's when we detected that the component was being used in a new or different way, basically being used more strongly. That's indicating from our algorithm that there's something unusual going on here, and this was about a year before the 2018 eruption. So flag it as a volcano you should look at in more detail. But we've got a new algorithm, and it's called Lix Alert. We've gone for Lix Alert because we started this when I was a PhD student and I was funded by the Looking Inside the Continents from Space, or the Lix grant. And to do this, I'm going to have 4 changes that we brought through from our prototype. I'll talk about them today. One is increasing the variance of deformation signals so we can recover them. Secondly is a bit more carrying on from what Susie said about can we do ICA temporally now? And then I'm also going to introduce a few tools for visualizing lots and lots of volcano monitoring results using Lix Alert and our results from applying it globally on the Jasmine computing service. So to start, we've had a quick look at some Campi-Flegrei data. Top left, I show a really shaded DEM, and top right is the output from the LixBAS processing. It's a pretty simple, clear deformation signal. We've got a few pixels of interest. On one of those, the orange pixel, located on the deforming region, we can plot a time series for. So in terms of volcano monitoring, I'm not necessarily interested in looking at the deformation pattern so much, but what I am interested in is the change in rate of the deformation pattern. It does speed up and slow down. And when these signals do speed up or slow down, that's the kind of thing that indicates this is a volcano that's doing something different, and perhaps you should go and look at it. So to get independent component analysis to work at Campi-Flegrei, we had to change how we calculated our displacements. Instead of taking just the Lix Alert standard, the Lixar standard short temporal baseline interferograms, we then found that actually we got better results when we maximized the deformation variance by calculating everything relative to a first acquisition. We did look at the rather time-consuming step of calculating all possible deformation between all possible acquisition pairs, but it didn't really improve things, and it did take a lot longer. So when we do apply independent component analysis to our new network, then we have independent components on the top, and to really see what those are, we tend to plot the correlations with the DM on the second row, and how they're used to reconstruct interferograms of different temporal baseline in our training data. So how strongly was that component used when you want to reconstruct a 2, 4, or 600-day interferogram? So in the Campi-Flegrei case, you see one component which is not in any way correlated with the DEM, but it is correlated in time. You see other components that are correlated with the DEM, but not correlated in time. So we think one's deformation, one's topographically correlated atmosphere. We can then switch to our main Lix Alert figure, which uses these independent components and then monitors the volcanoes using them. So on the left, we've got the independent components and also the DEM, just to give it some georeferencing. We can take a baseline stage of 1 or 2 years, so that's both cumulative and incremental interferograms. And then we do a really simple inversion to reconstruct each interferogram using the independent components. So you could think of independent component analysis as a super efficient encoding. You could have a time series of hundreds or thousands of interferograms. But if it truly comes from just a few components, such as atmosphere or deformation, you should be able to condense the whole thing down to just a few independent components, and then you can then reconstruct any interferogram using combinations of those. So that's what we show in this simple inversion point by point. We also, at the bottom, plot the residual. How well can we reconstruct each interferogram? The idea being that we should be able to do that well if we're capturing all the processes that are in our interferograms. To see how these are used through time, we just fit simple linear trend lines and then plot how far points lie from that trend line. Warmer colors indicate a point that lies a long way from the trend line, and that's something that's perhaps unusual or unexpected. So I can run the monitoring for Campi-Flegrei. You can see the new interferograms come in, do our inversion, see how well it's fit. Back in the day, I would have shown the whole of this thing, but I'm going to jump ahead because we just have so much data now. It's so temporally rich, and you have all these time series, all these time steps. So on the top one, we had our deformation component, and in orange or warm or going through to red points, we flag when points lie a long way from these extrapolated lines of best fit. And that indicates that the component's being used in a new or different way that we didn't see in our baseline stage. So that's what we're hoping to do at Campi-Flegrei, to identify when existing deformation changes in rate, speeds up or slows down. The topographically correlated atmospheric phase screen sees a really nice seasonal variation. It'd be much better fitting this with a sinusoid, and it's nice to check that that comes out in a result that we'd expect. You do see some false positives in the residual, some points that lie a long way from the lines of best fit. And when we look at those individual interferograms, we tend to see a really strong, unusual turbulent atmosphere in that interferogram. If you haven't seen a turbulent atmosphere like that before in the baseline stage, you can't fit it well. Therefore, you get a high residual. But we handle that by summing the residual per pixel and then averaging for each interferogram. So when you see an unusual turbulent atmosphere, when you are able to make the next interferogram, when that becomes the second acquisition in it, you tend to see a sort of sign flip of that. And therefore, when you're calculating residual per pixel, it disappears. So our algorithm does flag these with red, but then it goes back to cancelling them instead of them being prolonged periods of marked as red. So what about stratovolcanoes? That was the next thing. We know that when we move away to different volcanoes, we're going to have more challenging cases. And independent component analysis often works poorly here. And I think there's you could write a whole essay on this, but I think that one of the big issues are how non-Gaussian are your signals in time or space? Should you be applying it temporally or spatially? How independent are your signals in time or space? For instance, atmosphere and deformation are definitely independent, probably independent in time. Actually, we've had some talks that suggested that maybe atmosphere can have more of an impact on these things. But spatially, if you have a stratovolcano with a big topographically correlated atmospheric phase screen that's located on the cone, you could also have deformation located on the cone, so they're no longer independent. And the last point, I suppose, is a sort of computational one. We have really asymmetric data in terms of time or space with INSAR. We might have tens or hundreds of thousands of pixels, but we might only have tens or hundreds of times. And that has a really big impact on the independent component analysis algorithms when you're iterating through in space or time, how many steps you get to iterate through and try and find your unmixing matrix. So a really quick synthetic example from an old paper. At the top, we have two sources. One is deformation and one is topographically correlated atmosphere at Vesuvius, and they're offset by about 6 kilometers, which is shown on the vertical axis spatial separation. At the bottom, spatial separation drops to 0. Your deformation is located under the cone, the kind of challenging thing you could get. If you look at how spatial independent component analysis works, you get an expected result when they are spatially offset. It works well. But if you put the two on top of each other, breaking your assumption of statistical independence, then you get really poor performance. And this is where you think that maybe switching to temporal ICA could be better. So to do that, we took a time series processed with Lixbas at Vesuvius. From 2018, the big change is we just have so many more acquisitions. From having probably less than 100 acquisitions, we've now got nearly 300 in this time series. And that gives us computationally a much easier time when we're trying to estimate in time independence. So top left, got the DEM, top right is the cumulative interferogram for the whole 7-year span. You can see that at the top of the volcano, there's quite a lot of incoherence, but we put an orange pixel of interest just to the left in the figure, at least, of our maximum deformation, which you can see in blue. So that's about 15 centimeters of motion away from the satellite throughout the time period. And there are GPS receivers up there, so you can go and have a look and see how this compares with using that as ground truth, and they see the same substance signal. If I plot a time series of these points, the orange point, you can see you do have the subsidence, but stamped on top of it is something you'd be better fit with a sinusoid. And this would really be challenging for us to monitor, because when you do see points starting to go upwards, has subsidence stopped and we've now got inflation? Is this a volcano that's doing something really unusual? Or perhaps you're just working at something that's a mixture of deformation plus atmosphere. So these are results from our independent component analysis, but now switched. So we're looking for temporal independence, not spatial independence. So these are components that are used temporally independently throughout the time series. You have one component that's not used very strong, doesn't correlate well with the DEM, but does correlate well in time. That's on the lower plot. Whilst you get another component which is very strongly correlated with the DEM and no correlation in time. What also makes me think, or us think, that that's topographically correlated atmosphere is if you look to the east on the right of the figure, you can see that you do get a lot of incoherence where there's hills there. But you do also see this component featuring quite strongly. So probably something to do with topographically correlated atmosphere again. If you look at the full Lixalert figure, then now our deformation pattern has a pretty much just linear trend. We don't see any of that seasonal or sinusoidal signal on top of it. The atmosphere, on the other hand, does still have some subtle sinusoid, and probably it's actually split between two components because it is a bit of a challenging one. So from a volcano monitoring point of view, this isn't super interesting because there's not really any unrest characterized at this volcano during this time. But it's nice to test our algorithm and show that we're not getting false positives. So after this, I didn't really know how to sum this up with a slide, but Richard Rigby took our codes, implemented them on Jasmine, and we go from running on 10 or 15 test volcanoes to about 1,000 volcanoes. And what makes this even more challenging is some volcanoes are in multiple Lixar frames, and then you've got ascending and descending look angles. So suddenly you get an email from Richard, he says, hey, all your jobs are finished. Here's a directory of 3,000 volcanoes, and each one has a figure per time step. And hidden in there are interesting results. So this is La Palma. On the left, we've got the independent components, and they're probably all just atmosphere, I think. They correlate really well with the DEM, you can see. The kind of thing you'd probably expect when you stick a big lump of mountain in the northeast trades that you get blowing through the Canaries. But what is interesting is that when we saw the 2021 eruption, there were new deformation signals associated with that. Because we'd never seen them in our baseline stage, this was something that our algorithm flagged up with the red points and the last point with the high residual, because it's saying that this is doing something unusual, perhaps you should go and look at it. So how to visualize these thousands of results? There's interesting things buried in there. How can we do it? Well, we thought we could condense our time series, our Lix alert figure, into just 2 values per time. So a 2 by t, where t is the number of times matrix. We just have 2 values. One was for change in existing deformation, and one was for new deformation. But first, to do that, we'd have to take our independent components, work out which one was deformation. It's not always the top component that I pull out. That's the case at nice or interesting volcanoes, but not always the case. So something that we did to address this was we used a deep learning model that Andy has already introduced, which can classify or locate deformation. And traditionally, this is, we've applied it to interferograms, and this is, I think it's the same figure that Andy showed, actually, or parts of it anyway, showing how you can use it to look at, say, on the left, a deformation pattern that was at Wolf, or in the center, something that's actually an atmospheric pattern, and at the right, something again that's a deformation pattern. So the deep learning model was great, saying which independent components are which. If we then go back to Sierra Negra, this is with our automatic processing on using the LixBAS time series on Jasmine and our Lixalert results, we can now say that IC0 is capturing most of the deformation. And I would just draw your attention, I suppose, to the vertical scale on the right-hand side of the axis. For this, it goes between 0, minus 0.5, and about -1. So while some of the other features do have nonlinear best fits through them, they're probably a lot smaller. So most of the deformation is captured in 1. And if we want to look how that changed, we can plot that on the X. And then if we look at our residual, which we think indicates if we've got new deformation we can't fit with our independent components, let's put that on the Y. So I can start monitoring. We click through in time, new interferograms come through. And in the case of Sierra Negra, I've already showed that when the deformation increases in rate, you start using one of the independent components differently. That means that the lines of best fit and the points have a large separation, many standard deviations, which we express in sigmas, and we start plotting in the bottom right corner of our plot. When the volcano erupts in 2018, you see some really interesting deformation, which we can't fit because we've never seen it before, and our algorithm now flags these points up in the top left-hand corner. Jumping to a different example, we could take Erteale. In this case, our baseline stage probably only has atmosphere in it. We don't think there's any deformation in these. So when you start monitoring, clicking through, ingesting new interferograms, recomputing your time series, when you do start to see deformation associated with the 2017 eruption, you can't fit this very well because you've never seen it before, you've only ever seen atmosphere. The residual spikes, that's in the bottom plot, you get warmer colors, and our points on the 2D plot start to go up the y-axis. Not quite as far as with Sierra Negra, but still enough for you to think this is something I should go and look at. So I've shown you a specific volcano for all times. If we want to keep our two-dimensional plots manageable, we could switch and take all volcanoes at one time, and then this could be an animated GIF, but it just gets too much going on with 2D volcanoes moving all over the place. So anything that plots in the right-hand side or the upper side, or especially the upper right, is something that we think you should go and look at. And we take thousands of volcanoes, which is every single point, and condense this down to a few volcanoes that you, the volcano observatory user, anyone like that could go and look at in more detail. So for instance here, the first thing I would go and look at for this week's summary is tar. I'd probably go and look at some of the other ones too that are labeled, but the points down in the bottom left, hopefully if our algorithm is working well, these are volcanoes that aren't doing anything unusual at the moment. Sadly, what we're finding is that if you do go and look at some of these time series, you tend to see that actually errors in our LixBAS processing get picked up really well by the algorithm. So it's a mixture of the challenges of automating LixBAS on a big scale. So what next? I think we'd like to improve the quality of our LixBAS time series. And I think one of the best ways we could do that is collaborating with the Comet Volcanic and Magmatic Deformation Portal. They've got really great LixBAS time series. We're working on LixBAS time series. If we work together, we could use some of their brilliantly quality controlled data, which we don't really have at the moment. We're also looking at a web-based interactive Lixalert figure. This is in beta at the moment, and then at some point, hopefully we'll deploy it on the web, maybe on the Comet Volcano portal. So if you've got a volcano you're interested, you can go and see our figure for each time step, or you can look at the overview figure and say, are there any volcanoes that are doing something unusual at the moment that I'd like to go and look at either on Lixalert or use my own data in more detail? Also, we absolutely love it when somebody uses the code on a volcano that they're doing a case study on. You probably know a lot more about that. You definitely know a lot more about that volcano than I do. And we always learn things about how our algorithm is working or not working. So all the code is on GitHub. And if anyone wants to use it, I'm always happy to answer questions or raise an issue on GitHub. So thanks very much. I'll leave my conclusions on the last slide and I welcome any questions.
Thank you. So you're starting with what? With geocoded, unwrapped interferograms?
Yep, geocoded unwrapped interference.
And filtered or not filtered?
Filtered as part of the standard processing by Elixir. That's Goldstein filter.
Okay. Okay, so, and could you do some of this stuff also with wrapped interferograms?
I've never tried. I don't know if anyone has used independent component analysis with wrapped data. It'd be interesting to know how the fringes shifting might bring the independent components being different for every single position the fringes are, but it's not something I've tried, but it would be interesting.
Yeah, everybody talks about unwrap errors. We know more or less what we are looking for. So if we can start with wrapped interferograms, maybe that's better.
I think one of the things that I really struggle with deep learning is remapping your data into the kind of value range that you can use with deep learning. So deep learning wants your inputs or outputs in the range 0 to 1 or maybe -1 to 1. And that's because of the activation functions and how they work. When you start working with unwrapped data, that's so challenging because we have an open-ended set of maximum deformation values, and it can be really hard to work out how you rescale things with big signals or small signals into this interval. But what I think would be great about wrapped data is you know what your interval is, it's always the same, and you are condensing into that same range. So I do think there's a lot of merit to working with wrapped data in the future, especially with deep learning.
Any other questions for Matt?
Not, can I ask, and the resolution influence a bit the result? Because Andy was saying that 30 meter is better than 100, so.
The big impact is it's definitely more computationally difficult. It's much more computationally difficult to do fast ICA, which is part of the ICA package we have. It's not something we've tested at the moment, but I think it probably will improve things. It probably will improve things. In the simplest sense, when you're working spatially, more pixels means more step to iterate over your data in much the same way that I said more temporal richness is really useful. So more pixels in that respect give you more chances to update your mixing matrix, and that should be really useful for the algorithm.
Other questions?
Okay,
Thank you.
Thank you.
So we can move to the last one. You, Rotterdam, Clara. Was correct. So we will move to Canada.
Yeah. Hi everyone, my name's Drew Rotherham. I'm an Earth observation scientist at the Geological Survey of Canada, and I'm going to be talking about the volcanic risk reduction program in Canada and our progress towards an operational INSAR monitoring system for the Canadian volcanic hazard. It's really humbling, actually, hearing all the presentations and seeing everything that's been done with Sentinel and Elixir, because I feel like we're definitely playing catch up. We've only kind of really recognized how threatening the Canadian volcanic hazard is recently, and we spent the last couple of years trying to develop an INSAR system based on RCM. So volcanism in Canada, yeah, when you talk about Canada, most people don't really think about volcanism. You think about snow and hockey, but there does exist a non-zero volcanic hazard. So essentially, it's mostly on the Pacific margins. So we've got the chain of volcanoes that continues up the Cascadia subduction zone, and it goes through Oregon, it goes through Washington State, and there's no reason that it stops at the border. It actually continues right up through British Columbia, through the Yukon, and right up into the Aleutians in Alaska. So here's kind of a map on the left showing most of the volcanic cones that are known. And here's an example on the right of an air photo from our trusty Cessna 172, showing kind of what the volcanoes in Canada tend to look like. And I think part of the reason they've been commonly underestimated for so long is, well, there's a number of reasons. But I think a major one is our volcanoes don't typically look like your typical menacing stratovolcano. They're mostly glaciated. So if they erupted prior to the last glacial maximum, they've been heavily eroded. There was a lot of eruption during deglaciation, and there's some eruptions during glaciation, and so they've got really atypical structures. The other, main reasons they've been commonly underestimated is there's been no monitoring. So if you don't see any volcanic activity, you don't really think about it. And there hasn't been any volcanic eruptions in Canada in living memory. So in the 90s, when a lot of these volcanic cones were mapped, there's 348 known vents in the Pleistocene age or younger, and 54, that's a minimum bound, 54 are known to be active during the Holocene. And so a couple of notable events, 200 years ago, there was, approximately 200 years ago, there was an eruption at CX Cone, which is right around here. And a little over 2,000 years ago, there was a major Plinian eruption at Mount Meeker. And that was, the ejecta from that eruption have been found as far east as the other side of the Rocky Mountains, which is like over here. So it was a pretty major Plinian eruption. Another notable event was a 2007, 2008 seismic swarm at Nazca Cone. And I did say that there hasn't been any monitoring, like there hasn't been any systematic monitoring, and that was actually found kind of fortuitously. There was an exploration group doing seismic, and they just sort of noticed that it's a seismic swarm. And then the emergency seismic team kind of mobilized and monitored that event. So at any rate, based on past eruptions and evidence that's there, the annual probability has been estimated at 1 in 200 for any eruption, and 1 in a little over 3,000 for a major eruption, which is kind of on a similar scale as Cascadia megathrust earthquake. So in 2021, the GSC published an open file where those events that I talked about previously were lumped into 28 distinct volcanic fields and complexes. And a threat score was assigned to all of these using the USGS methodology for the National Volcano Early Warning System. So they use the exact same methodology to assign threat scores, and which may have been surprising to some, but a bunch of the local volcanoes, so here's Vancouver, where I live, right here. A bunch of the very local volcanoes ended up having high or very high threat scores. And so some of the things that drive these threat scores are obviously proximity to infrastructure and population centers. And another thing that drives them is obviously recent eruptions or current evidence of unrest. So I think it was in 2013 or so, there was fumaroles that were noted to start off-gassing at Mount Meeker. And Mount Garibaldi has had several several eruptions that are maybe around 10,000 years old, but it's so close to population centers that it really drives up the threat score. Melcali itself has a number of hot springs that are not monitored at the moment either. So with that threat ranking, you can see here, this is kind of the portfolio of Canadian volcanoes. We've got 2 really close to population centers that rank in the very high threat range, a whole bunch that are close to, or some a little bit further away from population centers that rank high, and then a few in moderate and low. And here's kind of how they stack up compared to American volcanoes. So we've got Meager and Garibaldi using the exact same methodology, kind of right up there with Mount Baker and above Yellowstone, certainly. So, like I said, up until about last year, Canada had no real dedicated volcano monitoring system in place. We didn't have seismic stations or routine gas monitoring or any of the bells and whistles. And the U.S. recommendation from that NBUS report that I was talking about before recommends minimally a remote sensing approach for volcanoes that rank low and above. So, of course, we would like to put all the instrumentation in the world, GNSS and seismic stations over our very high threat volcanoes. But since we're kind of starting at square one, we decided to go first with the remote sensing approach, where we could just at least cover and have some form of routine monitoring, and then use that remote sensing approach to, if we did start to see some unrest, to justify the added expense and complexity of instrumenting these volcanoes. So here's what we set out to build early on, really quick. So we wanted to make an fully automated volcano INSAR monitoring system. So starting with CSA infrastructure, which is RadarSat constellation mission satellites in orbit, they get all those imagery, obviously get downloaded and stored in a persistent storage. We access it via the CCMEO API, and this is kind of what we want to start building. So, an automated processing system, persistent storage, and a front-end UI. And yeah, so we don't want to exclusively use RadarSat constellation mission, but it is a source of secure and domestic data that we can rely on, and we know it's going to be acquired routinely and at high resolution. And so this is kind of the backbone, this is the workhorse of our data flow. It's a constellation of 3 identical satellites, and a lot of the talks, I don't know if people know about RCM that much, but a lot of the talks have really been about Sentinel, and maybe I've seen some RadarSat 2 data at this conference, but I haven't really seen, I don't think I've seen any RadarSat constellation mission data, which is disappointing really, and I think is a huge gap in potential. So this is the 3rd generation of SAR programs, RadarSat 1 and RadarSat 2, and RadarSat 2 was used a little bit more and more for INSAR, but largely these were used by D&D and Canadian Ice Service and users like those. So it was launched in June 2019, so we don't have those super deep stacks of data yet, but they're on their way. We're slowly acquiring. It's C-band radar, a lot like Sentinel, but the difference between RCM and Sentinel is we tend to collect over our volcanic hazards at 3 to 5 meter strip map mode. So we typically use 3 meter if we can. If the footprint's not big enough for 3 meters, then we'll switch to 5 meters, or maybe we'll use a couple of frames of 3 meters. But what the really big difference is, especially from RadarSat 2, which had a 24-day repeat, is we collect data at or up to 12 days repeat pass. So in kind of low priority periods, we collect at 12, but sometimes we're often enough, we're actually able to collect 4-day repeat, which has a number of implications, especially for INSAR with fringes and coherence. So when we set out, these are the guiding scientific and development principles. We wanted to align as closely as possible with the open science and open government policies as defined by the Treasury Board of Canada. So typically, as government scientists, we're supposed to do everything out in the open and make as much as we can open source, which has been made really difficult by the protected nature of RCM data. And of course, it's a little bit different with Sentinel, where Sentinel is free and open source and open access. RCM is still kept a little bit under lock and key, which is unfortunate, but it's just the way things are. We want to make everything cloud native, but portable. So we ended up building a lot of things with containers. So everything right now runs on AWS, but there's no reason it couldn't be ported over to a physical server or to Google Cloud or Azure. And from the outset, even though we wanted to rely heavily on RCM, we decided to still make it sensor agnostic. So we've built in the flexibility to process RadarSat-2 and TerraSAR-X. The processing Sentinel-1 seems a little bit redundant at this point, but we've still got the capability to do so. And we relied on iterative development principles. So we started with kind of a minimal viable product. We raced to that within a few months. We got that going. And then we've kind of been building out the bells and whistles as we go. So here's a basic cloud architecture. I'm not going to dwell on this too long, but essentially we have a fully automated process where we check for new imagery daily, and that kicks off a simple queue service that tasks a job. We've got a persistent storage, and that automatically spins up the compute resources we need. We crunch through all the interferograms, process them, we destroy the compute resources, we store everything in persistent storage, and then we serve it to our own dashboard using WMS services. So this looks very cloud native and it looks not portable, but there's no reason that any of these functions couldn't be simply, almost every component that we use in AWS has got an analog in a different cloud provider or something that we could use on-prem. So here's kind of in the first year, our first attempt at a dashboard. So we've got kind of a situation, a national overview of everything we see in the volcano portfolio of Canadian volcanoes. And so we've got listed the most recent SAR image. So this is, I took a screenshot just before I left on Saturday. We just sort of maintain a volcano status of if we've observed any unrest or not. So, we're just sort of doing things a little bit manually at this point, but as we mature and get deeper stacks, we want to get a little bit more complex. And seeing all the great work by previous presenters has given us a lot of inspiration moving forward. So yeah, we've got a kind of an overview page and a detail page for each volcano. This is kind of what our analysis platform looks like. So we've got a coherence matrix on the left, and I see a lot of these kind of as diagonals, but we decided to flip it 45 degrees. So instead of date, we've got temporal baseline versus primary image date. And we've got different GUI components for baselines and things like that. So we can kind of go through here and manually kind of inspect, which is still feasible at this point because we've got so few images and so few sites, but as we scale up, that's going to become less and less feasible. We're getting better at atmospheric modeling correction, but it's still a bit of a pain point for us, as it seems like it is for others as well, so that's comforting. So that's essentially where we're at after 1 year of development, and maybe I'll just go into some examples of what we've observed over the first year of running the system. So somebody told me more than once, if you start looking at INSAR stuff, you'll start seeing stuff, and we did. And so here's some interesting, I've just got a few interesting observations. So we've seen really massive slope deformation of Mount Meeker. So in 2010 was one of the largest landslides in Canadian history. It happened on the other side of Mount Meeker. And last summer, we kind of noticed that, and this was when we first started running the system, right away we started noticing these deformation anomalies. And so this slope, which usually moves at maybe 2 or 3 centimeters a year, started really accelerating. And it happened to be a really hot summer. So it was, the hypothesis is that, there's either glacial melt that's driving and making changes to the groundwater regime, or perhaps even frozen ice underneath that's holding the slope together. But as we get warmer and warmer climates, these are going to become more and more of a problem. So even for RCM, a 12-day repeat at 3 meters, this was moving so fast that we couldn't even wrap it by the end of July. Fortunately, it started decelerating as the temperatures cooled, and it didn't lead to a catastrophic failure, but yeah. Other interesting observations, we started noticing a lot of subsidence of lava tubes at Mount Edsiza. So these flows are, I think, 1,000 or so years old. They're not very vegetated, which means they've got kind of fabulous coherence, throughout the year. And we started noticing kind of these sinewy patterns, and we shopped it out to all the geologists at the GSC and kind of crowdsourced an opinion what they might be, and the consensus seemed to be collapsing lava tubes. Kind of interesting, but not really a volcanic hazard unless you're trying to build a pipeline or something across it. But one thing we did observe in the first year was magmatic unrest at Mount Edgecumbe. Now, we weren't the first people to see this, of course, but we were able to collect INSAR measurements over the winter period. So that's one thing about RCM is the 4-day repeat. So here's a 4-day pair from January 5th to January 9th. And it's usually a time of year where you expect pretty garbage coherence. But with such a short time between acquisitions, the temporal decorrelation doesn't really have enough time to take effect. We haven't got a deep time series of RCM data over Edgecumbe yet, but we were able to take a look at some of the RADARSAT-2 spotlight data over the same site. And we've got ascending and descending spotlight, and these are both approximately 1-year pairs, but we did process the full network, unfortunately, at a 24-day repeat. And we did notice quite a bit of both uplift and subsidence in the line of sight on the ascending and a lot of subsidence on the descending. So since we had ascending and descending, we did a quick 2D decomposition, and we noticed that, as you might expect, a lot of horizontal movement kind of on the flanks and a little bit of vertical movement near the center of the edifice. This was originally in a paper by, I think, Grapenfen and al., and they noticed about 8 centimeters of deformation per year. The time series was very linear, and one thing we noticed was we weren't seeing quite that much, but we were getting a lot more variation in our time series, so we were getting a lot more changes in rate. The other thing is, since we've got spotlight data and the footprints are so small, almost certainly a reference pixel is probably, or a reference zone, it's a reference region, is probably within the movement zone. So I would expect that we're definitely underestimating this deformation. But we're not too concerned with time series yet because we're just trying to get a fringe detector at this point over all volcanoes. So that's kind of where we're at currently. So we're running fully automated. We're generating new INSAR measurements daily. We've got some deformation phenomena observed in the first year, but we still have a lot of work remaining with better atmospheric corrections, automated detection, and we'd like to really scale up our deformation time test cases. So our plans for the future are to grow a training data set of natural fringes, and also grow the number of volcano sites that we monitor globally. So if anybody has any interesting sites, I would love to hear about them. Please get in touch. Yeah. And yeah, so I'd just like to give some acknowledgements to some of the folks at the GSC, Canadian Hazardous Information Service, DRDC, the Canadian Space Agency, and CCMEO.
Thank you, Drew. We've got time for questions. Marco? Pass the parcel.
Is it working? Okay. So I'm your counterpart a few miles down the road in the outer Vancouver as of 3 months ago at the Volcano Observatory there. And we would love to have RCM data for our volcanoes as well.
When you say Vancouver, do you mean Vancouver?
Washington.
Washington, okay, good. All right.
Have you gotten any good results in terms of coherence on the volcanoes in Canada that are more likely to the ones that we have?
Yeah, surprisingly, we didn't think that we would have great results over the winter. Fortunately for us, the winter is a less busy time. So the RCM constellation is fully tasked right now over Canada. The rest of the world, it's undertasked, and there's a capacity for other sites. But over Canada, it's fully tasked, especially in the spring, summer, and fall. Over the winter, it's generally not fully tasked at all, and that's when we're able to get really dense 4-day time series. We get bumped sometimes outside of the winter. And so with that 4-day time series, maybe we're bouncing off of snow. I can't say for sure, but we're still able to maintain coherence with those really short temporal baselines. So yeah, we do get pretty decent data in the winter.
Good to know.
I think Andy has a hand up.
Yeah, thanks. That was really interesting. I mean, I guess the reason a lot of us, or at least I haven't really looked at RCM data is because of where the data are mostly acquired. So I didn't know it was an option to actually, is it an option for us to request data elsewhere or?
Well, you'd need a partner within the federal government.
Right.
So RCM's fully dedicated to Canadian scientific purposes. Scientists within the federal government do have the capability to task. External partners don't. But if you have a partner within the federal government, yeah, it's totally. You won't get the same priority as some of the more stakeholder users, but it is possible putting background taskings for sure.
Okay, but is a federal employee of Canada likely to kind of want to look at a volcano somewhere else outside of Canada?
If there's a scientifically justifiable case, such as observing deformation that may be in the same style as Canadian volcanoes, so that we can learn more, then yeah, I think there could be a scientific case. Yeah.
Other questions?
Okay, let's close that session there then. I think there's some good material, particularly in this last talk, which will be relevant to the roundtable, which it's not scheduled to start until 10 to 6, so we should probably keep the time in case other people want to join us, but please stick about and contribute to that. And if anyone wants to chip in on what the seed questions should be for that discussion, come and talk to us in the break now as well. Thank you.
Thank you.
Yeah, okay. Paul's suggesting a 5-minute break, and then please everybody come back. Yeah. Yeah. Well, so we have a slide, I guess, to show together now. How can I get something on that? Is that a laptop or is it the PC? So I could just put in a memory stick. Yes, okay. Sorry? So basically, that's all I've got. Yeah.
Yeah,
Do you think we want anything else? This is the thing that you said provide.
So I think mission about volcanoes. Yeah, it's kind of the new one and
Right.
complementary. I was thinking about like benchmarking, wondering like if we are in a,
So we'll keep the rest of the hang out somewhere outside.
Yeah, please. I mean, all come and do the talking. That's true. Yeah. I mean, I thought I would just kind of stand and hover and type things anyway.
That sounds good.
Yeah.
The typing thing.
Yeah. Well, I already volunteered Fabian for doing the reporting
I'm
back,
gonna
so I
do
feel
the
like the least I
report.
can do is the typing.
Oh, excellent.
Right, so you're good. You're good. So yeah, I will be here, and that's yeah. So I was wondering if,
Something about benchmarking.
yeah. So the benchmarking, there is, I mean, different level of benchmarking, right? It could be, I mean, we have been talking about that, comparing like processing chain, about there is the insert processing, but now there is also like, many groups and many different people are developing anomaly detection and
So I could say, do we need benchmarking for performance?
so yeah.
I mean, processing, time series analysis,
Yeah,
machine learning.
yeah, exactly. Just have, when you want to compare your performance when you're developing something to things that already exist. Having
Good
kind of-
idea. Time series, machine learning applications. Okay. Oop, I can't spell or type. Formatting.
And the harmony, probably people will also,
They will have some input.
some input on harmony or just some thought about harmony.
So let's just move this onto the computer and put it up on the screen then. There. Fringe 2023.
The only thing is everybody, in other rooms, so this is not that be interesting.
It's not confidential.
How is the channel getting so much?
Yeah. All right, it should be coming up now then. Yeah, I was trying to get them onto this computer, which proves hard. I added a little bit, whether I mean they're not. No, not that. Yeah. Okay, on that computer.
Yeah,
But fine. I added something about DRR.
yeah, I just thought it was important. I don't really care how we phrase it.
Right?
I think, yeah, well, you've
Rather
all
like
done this a
capturing
lot.
the
Stuff. Yeah. Paul? Paul? You've got the slide up.
I know, okay.
You want to live editing?
I will try and type, not so everyone can see my typing, because I'll inhibit my typing, but,
Just put that, yeah, this is the screen that's being shown up there.
okay. So if you,
Yeah, I don't want me to type and you can talk.
I don't mind, I mean, you're volunteering for time.
Volunteering to type.
Oh, brilliant, okay, yeah.
Well, if you're right, sure. I think so, yeah. Yeah, there's nothing you don't say. Yeah, I think they want to do like live edits. Yeah, like write it down, people see. I volunteered to type. Okay. Susie's in charge. I volunteered to type.
Okay. Okay. I will report on Friday.
Yes, I will. So, yeah, on Friday, is it supposed to be 2 slides for all of Volcanoes, or 2 slides for Volcanoes 1, 2 slides for Volcanoes 2, 2 slides for Volcanoes 3?
Previously, it's always been 2 slides of volcanoes.
Okay, oh, that's
Yeah.
good.
It will be, yeah.
Okay.
I think I did this one year.
And you're gonna do it?
Yeah, I mean, I can, I can report it. And we,
For all 3 sessions, or do you want us to feed in? Do it for all of it, that's great.
I think
We'll chip in for the
Yes,
content,
okay.
right?
Yeah,
it's
okay.
better, I can send over the 2 slides like before
Yeah,
Friday,
yeah.
or the
Yeah.
chair. Then if you have input,
We'll have them record, send it to you. Yeah, maybe myself, if anyone has input. Back. I've got a lot, I've got other people. Okay, we can do that. Not that it's left. Right, should we do this? Or a few minutes early, yeah?
I can text down. Oh, yeah. True. And we can hand around the microphone, I guess.
Yeah. Make sure to start probably like. It's 20.
I thought it was later. There's a queue for the news.
Oh,
There's 2.
yeah, there's a problem with this building actually. There are some on each floor and there's some in the basement.
None of us know where to look. So.
Then there are some not obvious. Like one. Yeah, it's a stupid building. Yeah, it's like heritage property.
It's not whatever the content podcast.
Not that I've heard. I kind of imagine people working on what you never know.
It's not university.
You're very like on brand.
it was good to see the ongoing picture, like,
Yeah.
animated picture. And,
Yeah, we have to make it work. Yes. Yeah, it's kind of been like a great maternity. There's all these old things that are really mature now, are really well developed, and then a whole bunch of new things. And normally there's not such a clear like line. Normally you kind of new things are coming on as you finish up the old ones. But maternity really when you clear split.
Yeah.
Yeah, and I think you should chat with the posters.
yeah. So I was a bit on my poster on Tuesday, but I want to look at
Or Nicole?
You didn't take the edit, but you delivered it. Disaster risk is not insult. Rather than typography, I think insult.
Can you go down?
Edit.
Okay, and show maybe it's not front.
Can you, keyboard doesn't work, period?
Mouse works. I can move my mouse when I try.
That's not where it's protected view. Because they don't have anything else. Anything else. Okay, yeah, just because it was downloaded.
Just so you're aware, the doors of the Roger Stevens building, like the automatic sensor stops working at like, I guess, 5:30 or something. Okay. Basically, if people don't get in, they can't because the doors don't open anymore.
Okay.
We have to wait like a cleaner to come by.
I don't think it's a keyboard.
Okay.
So, just so you know,
Protected view on the
not actually get this event, it's not ready.
They should, you know how they have the people that guide us
This is like
where to walk?
a Fringe account.
Exactly, yeah, yeah.
Fine.
This is the flagging it.
Okay, great.
Yes, that's fine. Thank you. Okay.
Apparently the building closed at 5:30, so people wanted to rejoin this late, they can't get in the building.
All right, so, okay. All right. Should we send them
I can make it
I don't
fill
think
out.
it's gonna use it.
But I can't make it work.
Can you continue just to check?
We can also have could someone do us a favor? Apparently this building was locked at 5:30, so if anyone wanted to come in late to join this discussion, they'll be stuck outside the door. Do you think one of the Leeds PhDs could run down and just check? And if there's anyone accumulating there, let them in. Thank you. I guess it'll just be the one by the Fringe banner. Don't spend ages, Rachel, just if there are people there waiting. Thank you. All right, shall we start? Okay, let's kick off this the roundtable discussion for the volcano section. So the aim of this session is to have a discussion around the important issues, particularly things that we might want to communicate to ESA. And it's an opportunity to pass on recommendations to ESA from the community. So we've got a couple of seed questions to get us started. But if you have anything you'd like to add, please jump in and we'll try and record it. Juliette offered to capture the discussions and do the typing, and Fabian was going to report back on Friday. So I will let's start off with the first question, which is the same as it is most years, I think. How can these missions be optimized for volcanoes, meaning the current ESA missions and the future planned ones that we heard about on Monday? And we've added a statement asking about complementarities with other missions, like ALOS, SAOCOM, maybe RCM as well, if we can get the data. Does anyone have anything they'd like to start off with? Andy, thank you. Mike? Thanks.
Thanks. Yeah, I'm just going to start off with the obvious one, which is that for Roselle and Sentinel Next Generation, it would be great to have two looks acquisitions so we can get north-south motion as well. So I mean, I think every session should recommend that. Try.
Yeah, and you can probably add that as a kind of fundamental thing. We appreciate continuity in time series, and that's all still great, and we still want it.
But Andy, what are you implying they should go from, have both right and left looking? How are you going to get the north-south with, just by adding more satellites?
It's like what we have with Sentinel-1 in the burst overlap regions.
Oh, yeah,
but,
yeah.
But over the whole strip, so two looks everywhere. So just essentially increase
Okay.
the overlap. And it's feasible, but yeah, as was mentioned on Monday, or was it Tuesday? There's a downside, right, for other applications, but for us, it'd be ideal.
So is your recommendation for Sentinel or for future missions? Only for future missions, right?
Future missions, yeah.
Yeah.
So, but I guess it's feasible potentially with Sentinel or Next Generation as well.
I would say I would add a more mundane request. I heard something over lunch or earlier about that there's a question about whether Sentinel-1A, C and D would not be doing both ascending and descending each satellite. Somebody,
Yeah, so I was saying that. So it's more a case of how they divide ascending and descending, which is a problem for Harmony, but not a problem for Sentinel-1.
oh, okay, so you'd still have both giving,
Still
okay,
have-
just for
It
Harmony,
just
sorry.
depends which Sentinel they assign which ones to, because Harmony will only be on one of those. But,
Got it,
yeah, so I don't think that's too much of a problem for Sentinel, but it's certainly a problem for Harmony.
Okay.
Sort of another one too. So there is this plan to park Sentinel-1A once 1C and 1D are up.
Okay.
And it'd actually be quite nice to have that acquiring data as well, if possible.
Yep.
Right.
Good idea.
Yes, don't turn it off. If it ain't broke, don't fix it.
So I think we should make clear at the roundtable that the potential, I mean, we came to here to meet today and they said the potential what INSAR or what we with our community, Volcano INSAR community really have. So, As I said earlier, if we get daily images or half daily or hourly images, what eventually is going to happen, then the people at the Volcano Observatory and the Hawaii Volcano Observatory who are freaking out when there's a dike propagating, they have to try to image it as good as possible. And these algorithms which our community can develop, it can really solve the problem. So okay, that's the first thing what we should make clear. And then what we need is really good data sets. Sentinel and to develop these algorithms, multi-satellite data sets. So we need a few, well, it's somehow funny that I'm starting again with supersites, but we need a few volcano supersites where which should be driven a little bit differently than what we currently have, or the current geohazard supersites. They are driven by the volcano observatories, and okay, it just goes according to the needs of the volcano observatories, and they have to make sure that they get the data what they need. But what we need is really a few supersites where we get really as much as possible ICE-I, what is it called, capilla
space.
And I don't know how many data you can get with Cosmos Skymet now, but we should just shoot for one. Yeah, getting full data sets for a couple of volcanoes, really as good as possible, so that our community is ready when all these things like Rose-L and Harmony are online. Otherwise, these satellites are there, and we are just starting to develop algorithms. Well, you guys are doing it here, but many people will start developing the algorithm just by the time these things are launched. And then by the time the algorithms work, they're gone. So we should avoid that. If we get good data set right now, we can be ready by the time all these satellites are launched.
So are you talking about using current missions without open data policies as kind of an analog for developing things for nice RC? Or just saying that we really need all data everywhere?
We need, as much as possible. Yes. All, well, no, not everywhere. For a few sites.
Okay, well, so I guess but the context of the super sites was always that these are sites where there was a demand for the data scientifically. There was a scientific case to be made for having it, as well as a hazard case. And then there are the other programs like the CEOS Working from Disasters volcano programs, which are actually more kind of focused on providing it to volcano observatories. Are you proposing something different again to that?
Yes. Data sets to learn machine learning algorithms, to apply machine learning algorithms.
Okay. I mean,
one thing we're learning from developing machine learning algorithms is you need data from as many volcanoes as possible because they all behave differently. So focusing everything on a few supersites doesn't actually fill that need. So we're kind of back to all data everywhere all the time.
that'd be great. One
I
thing
think-
that
I
Paul
think we are
mentioned. Sorry, go ahead.
Not many people, we haven't, everybody is just using what we saw here, it's just Sentinel. But nobody is really combining all these different sensors, and that's what we're going to have in a couple of years. NISAR, Sentinel, whatever, ALOS, we don't do it. This machine learning or those things what you guys are doing, if you were using multiple satellites, it would get much better.
Yeah, I think absolutely. And the other thing that, is a constellation approach is also important in terms of latency and being able to detect changes that happen rapidly. And there's also a coordination question there. But I was going to add something to what Volk said before about commercial missions, ISI and Capella Space. And it would be great to have a pathway for commercial operators to provide data for hazards, which I think is not really there at the moment, although there's some kind of ad hoc relationships. I don't know if that's really a recommendation to ESA, but...
I think ESA have a lot of weight in things like CR, so it's a good
Yeah.
thing. Always a good thing.
Yeah, and they run third-party mission things for limited amounts.
With the current geohazard super sites, okay, the volcano observatories, they are happy and overwhelmed with the data they have. And we don't get all the data which is possible. And okay, that is because it is hazard driven and driven by the needs of the volcano observatories.
Yeah, and I think the other factor there is also the acquisition strategies behind the different missions, because of course, Cosmos SkyMed has the background mission for volcanic hazard, but TerraSAR-X, for example, doesn't.
Doesn't exist typically, or it's not optimal.
It's ad hoc.
And I mean, the other thing with, ALOS or ALOS 4, when it comes out, it's still going to have this very heterogeneous acquisition strategy. So I wonder, for sure it can be very valuable data for particular situations, but I wonder how, I guess maybe a service, something like LIX could handle a very heterogeneous influx of data, but it seems a lot of these systems are really designed for very regular acquisitions. So I don't know. When you're going down the machine learning track, I wonder how having a very heterogeneous set of satellites and types of data, how easy that is to implement.
But for me, it is the computer who is going to do it. Shouldn't be a big difference to, if it works for one satellite, you can do it with another one. And then you combine those different things. And that is then,
We couldn't have done this with NVSAT. So a lot of what we're doing relies on the reliability and the continuity of the data sets you get with Sentinel-1.
yes, but we could get with Cosmos SkyMed as well, or we do have, but not as good as it could be.
I think Cosmos SkyMed is the only other one we could probably do that with.
And I would imagine
RCM.
NISAR would be a good addition.
RCM might be good.
Yeah.
Because it will be very similar in terms of 12.
Yeah, so NISAR I think would work. But I should say, in terms of our deep learning, the CNN that I showed that's operational, it's basically a fringe detector. We haven't really tried it, but I would imagine that we could just feed any PNG file into it, and it would be just.
Yeah, I was actually going to put it here, but in the case if the problem really is the transferability of the model we developed training for Sentinel-1 to some other satellite, whatever difference that I have. Things like transfer learning, which we was already doing to build this thing, could very easily bridge that gap. You could have something that's primarily trained for Sentinel-1, and then you use transfer learning techniques with a little bit of extra training on radar sound, quantum sky, or whatever. I'm pretty sure we will get to that. We could do that from detecting those scans to detecting fringes in programs. I'm sure we can do it from Sentinel-1 fringes to radar sound, quantum sky, so it's not a huge problem, I think. Something that can be handled.
Should we move on to the next lead question? Does anyone have anything else they want to
answer before?
Oh, really? I think what you yeah. Do you want to have the microphone?
I don't know if it has been discussed before, but it would be a very particular recommendation to ESA regarding Etna volcano, because the ascending track doesn't have the proper cover over the entire edifice. But we have the border of the images just on the top of the volcano. And it's very particular, a very, very particular recommendation that, I don't know, if for ESA, it will work.
Perhaps.
But this is the swath boundary you're talking about? They can't do anything with that.
Yeah, but okay, I just said.
If you're on the burst overlap region, that's usually a good thing, because you get twice as much data from different angles.
Yeah, that's right. Yeah. But there are some issues also that we have with two different.
Does anyone have a? Oh,
Yeah, I don't know how to put that, but maybe Fabien can help me. But we should not forget about small-scale volcanoes. I'm thinking of Guadeloupe, which are hazardous. They're small and they are vegetated, so they pose a challenge to detection of any signal. But still, there is some displacement detected by GNSS, but apparently not visible on INSAR. So maybe we should not forget about not white swath, but small swath. And long wavelength that may be less sensitive to displacement, but less sensitive to vegetation too.
So L-band.
L-band, yeah.
Or ROSA, exactly.
But also a resolution issue as well.
Yes, yeah.
Also, yeah, many satellites now can go to meter or below, but those are not required globally. Yeah, one thing that I'd like to add onto that is for this like global, all these global studies, for a lot of these cases, they're still using a over 20-year-old DEM to process these. And I think that for a lot of these cases, when we need the high resolution, we should also very much have better and more up-to-date DEMs to accompany those. Yeah, hopefully Harmony will fix those issues. Yes.
Hey, while we're on the topic of Harmony and DEMS anyway, I brought this up earlier with over a coffee, but I thought I'd mention it now as well. So these DEMS, if we talk about the commercial options that are available, for example, from GeoServe, they produce these high-res DEMs, but then they spend around 8 hours per high-res DEM to clear up any artifacts and issues with those DEMs. So you have a good quality DEM that you can actually use for INSAR processing, which of course is not realistic when you are producing like over whole regions like the Harmony mission will. So the alternative that is being proposed at the moment is, of course, to mask out areas of noise. But then what you're going to do is you're going to have these areas of incoherence of masked areas changing for every acquisition. So then we're going to need some method of stacking or combining these different acquired DEMs over the time period to actually get usable DEMs for INSAR. Because as we see here, I think a lot of work goes into the let's say the dike modeling, the volcanic side, but it's relatively harder to actually really kind of like process the INSAR data on a very kind of strong level. So having consistent, good quality DEMs that can be used out of the box by the volcano community, I think will add a lot more value. So finding ways to fill these masks that is not just interpolation, because that will create other issues. You can't just layer the Harmony mask on top of, say, the Glow 30 mask, because then you're going to get edge artifacts, which are going to create DEM errors. So this really needs to be taken into consideration how we deal with this masking, so that you actually get a useful DEM for for INSAR.
And does someone who's connected to the Harmony mission want to reply to that?
I'm busy typing, yeah.
It's not just you.
Would say absolutely. And I guess what we've been focusing on is the time series of DEMs, where actually some of those issues probably aren't so important. But if you're thinking about a DEM for processing, but to make that DEM for processing, we would be able to use the whole year, probably be 2 years of the mission of DEMs, and absolutely then you can start to use stacking, etc. To do that. And DLR are really the experts in doing that. I don't think that is a problem, but it's certainly something we should request so they know it's a product we want to we need, something we really care about.
And it's definitely a priority for volcanoes.
Yeah. We need to make it a priority, but I don't think there's a problem.
And
Is the global DM still in there? More discussion about what there wasn't very information.
Okay, as far as I know, but maybe not. I missed. Like,
I remember.
The window. I couldn't miss this conversation.
Yeah, I think it was a while back, but yeah, there was a discussion at some point about whether the global, because I mean, Harmony is not going to be global coverage, of course, generally. So to make a global DM, it would have to be an extra requirement so I've got a feeling it was dropped. But
Okay, all right. Sorry, I'm out of date.
well, maybe it's back in. I don't know.
I think you're probably right. Okay. Apologies, I've been on maternity leave, so I missed a whole chunk of conversation.
But I mean, but maybe this is a recommendation.
Yeah, that's also what I think.
Yeah.
We didn't hear the recommendation.
Yeah.
The other one was dropped also for the infrastructure, but I think it should stress here that we need it for several years.
But I guess one question I have is, to what extent will Harmony be giving people, like, here's the data, do your own DEM, versus here's a finished product? Because with INSAR missions, it was kind of, here's the raw data, and then people would do their interferograms, develop techniques for improving things and wrapping. All that stuff was kind of left to the science community or engineering community to develop those add-on techniques to actually get usable data. So
yeah, my understanding is level 3 products. That's the plan, right? So actual, usable products.
On the other hand, it is an Earth Explorer rather than an operational mission, so they do want to make all the level 0, level 1 data available for scientists to do cool new things. But hopefully both.
I think that's right.
Okay, so we're kind of close to the allotted time for this. Does anyone have anything else that we should, any other topics we haven't covered that we should add in quickly?
So regarding what I said earlier, so just put something in, need 1 day time series to develop or similar to develop multi-sensor machine learning algorithms.
Yeah, I mean, maybe it could just be worded differently. You don't have to mention machine learning because then people indeed stuff, yeah. But actually being able to deal with, sort of fire hose of data coming in. It's important, I guess.
So I think that's currently covered by 3 different points. Is that?
Sorry?
It's currently covered by 3 different points, but rest assured we are going to go back and consolidate this. This is just my notes. Yeah, these are my notes. We will tidy it up, I promise.
There's another point there about benchmarking. I don't know if anyone wants to, do you want to add anything about that, Fabien?
Yes, I think it's a discussion that we had in the past to have just some benchmarking. And I'm wondering if, like with different groups are developing anomaly detection and on the time series, if we are like, it's mature enough that we have a benchmarking case that we can test performance, especially when we were to compare like different, of course, methods that can be compared. But it can also be benchmarking for processing, for unwrapping. We were talking about unwrapping this earlier. So yeah, I don't know your thought about trying to find benchmarking test site and have for comparison.
So in the past, I guess the ESA have funded into comparison studies like Terra Firma in the MBSAT days, basically into comparison studies. So that could be a recommendation that they thought, they ought to be funding an inter-comparison study. Yeah.
I mean, if we're directly recommending things for ESA to fund, come up with lots. I was going to say this issue of a kind of constellation approach to machine learning, or to that might be something that ESA could support in terms of building up the data set.
Yeah.
Okay, unless there's anything else that's burning, I think we should probably wrap it up to give people time to go back to hotels and get dinner and everything. But if you do think of anything that you want to add in, please email one of us. And Fabian's going to present this on Friday, and things can be added till then. And thank you. And thank you for everyone who contributed.
Yeah.
And see you at the posters.
I noticed when you showed your Bermuda countries, the amplitude was about half of what
Yes.
I observed. Now, are you doing any kind of atmospheric correlate? I know once I did, I running mid.
I don't remember what you don't.
I'll put in see what happens if I put in estimate a topo correlate atmosphere, and it reduced it, from 70 down to 30. Okay, it's throwing out a lot.
Well, the answer is no. The answer is these are quick machine learning experiments. They're not properly in the way that we would. I don't really know about lawyers, but we're looking at the good already. And the summer to summer, getting those really makes a big difference. As I'm sure you know, getting those that we haven't. If you look at Sierra Negra, also the really big deformation signal that occurred during the time of the eruption gets completely alien.
Yeah, I know that. I know for sure. Yeah.
It gets, and it doesn't know what to do. It can't unwrap it. So the time series just gets over it. So the really important thing, we know the time series aren't perfect. The point is not to make them.
Yeah.
But obviously the point is eventually to make them perfect. No, it's definitely up.
All right.
So I've written benchmarking study needs to be done centrally in G20.
Tomorrow morning. Yeah, so I'll come up with the
Yes.
So come here it's starting like
9:20.
Yeah.
In here and
Yep.
and conference auditorium.
conference auditorium 9.
Okay, so I'll come here.
1 and 2.
Yeah,
9 o'clock.
I'll come here first. If everything is okay, I'll come to this place.
I think it's okay.
Yeah, I'm sure.
Today
It's,
is fine.
double checking, making
I know,
sure.
I know.
Okay,
Thank you very
have a
much.
good evening.
Yeah.
Okay, nice.
I just yawned.
Oh,